Welcome back. How are you? Okay. Hope you are doing good and then understanding and then enjoying with the lecture. That's fine. Now, in the last session, we covered differentiator. In previous sessions, we covered integrator, and while covering integrator and differentiator, I explained low pass filter and high pass filter, right? Then we can use low pass filter as an integrator provided the frequency of the input signal is very much greater than fh. Then high pass filter can be used as a differentiator provided your frequency of your input signal is very much less than fl, right? That's what I told. But in the case of active integrator and active differentiator, we don't need any other condition, right? But if you consider op amp, the practical op amp, then we need some condition also, but I am not explaining, I am not going to those details. This is what is more than enough for us, okay? Considering ideal op amp. Let's solve few classroom problems. Problem number 12. Problem number 12. Write down. I think you have already. The op amp circuit shown in figure is a filter, the type of filter and its cutoff frequency. Therefore, it is given this is what, okay, asking for the type of filter, and if it is a filter, what is the cutoff frequency? That is what is asking. Option A, high pass filter 1000 radians per second. Option B, low pass filter 1000 radians per second. Option C, high pass filter 10,000 radians per second. Option D, low pass filter 10,000 radians per second. Is asking indirectly radians per second, not hertz. Okay, that is fine. Now, will you treat this as filter problem like RC circuit or op amp problem? See, blind technique, op amp problem. Treat it as op amp problem. If you know little bit about qualitatively the circuit, that is fine. But if you want to get the answer finally, treat it as op amp problem. Negative feedback or positive feedback? Negative feedback, right? Then virtual current concept is valid? Yes, valid. Then tell me what is this voltage? We don't know this voltage, right? Let me call this as VA. Then let me call this as VA, right? Try to apply nodal analysis. You'll get the relation between V0 and then VI. If you get the relation between V0 and VI, then try to get in S domain. If you are able to get in S domain, then we can use Bode plot to get the type of filter. And once you know the type of filter, we can get directly the cutoff frequency. Okay? Just listen. Therefore, let's apply nodal analysis. When you apply nodal analysis, let's apply here. VA minus VI divided by 1 by SC. I am taking it as SC. Okay? Plus VA minus 0 divided by R, where R is equal to 1 kilo ohm. Okay, R is equal to 1 kilo ohm. Okay, is equal to 0. Then what you get? You'll get SC into C, VA minus VI plus VA by R is equal to 0. If you take VA common, what you get? If you take VA common, SC plus 1 by R is equal to SC into VI, right? Then what is VA? VA is equal to, if you take R common, then VA, if you take R common, you will get 1 plus SCR is equal to SC into VI. Therefore, what is VA? VA is equal to, this R will go here, then SCR divided by 1 plus SCR into VI. Call this as equation 1. Okay. Now apply nodal analysis at the other node. Then what is that? This is first equation. Now the second equation. VA minus 0 divided by 10K plus VA minus V0 divided by 10K is equal to 0. Then 10K will be cancelled. It is nothing but what? 2VA is equal to V0. Therefore, VA is nothing but V0 by 2, or V0 is nothing but 2VA, right? V0 is nothing but 2VA. V0 is equal to 2VA. This is equation 2. Substitute VA, then what you get? V0 is equal to, therefore, V0 is equal to 2 into SCR divided by 1 plus SCR into VI. Therefore, what is V0 by VI? V0 by VI is nothing but your transfer function is nothing but 2 into SCR divided by 1 plus SCR into 2, right? What is this? Therefore, this is H of S. If you see the Bode plot, right, with respect to the frequency, then what you get? We have a 0 and there is a pole. Therefore, this is what your pole, right? Therefore, pole is nothing but 1 by RC in terms of 1 by 2 pi RC, and there is a 0. 0 is at 0. Therefore, according to Bode plot, if there is a 0, because SCR is equal to 0, SC is equal to 0, 0, and there is a pole 1 plus SCR is equal to 0, then SC is equal to 1 minus 1 by RC, that is with respect to root locus. But if you see in frequency domain, that is nothing but what? 1 by 2 pi RC, 1 by 2 pi RC. That is nothing but your this. Tell me what is this? This is nothing but high pass filter, right? This is nothing but high pass filter. And what is the cutoff frequency? This is nothing but your cutoff frequency. Your higher cutoff frequency or lower cutoff frequency. This is what is your, for low pass filter, this is lower cutoff frequency. FL is equal to 1 by 2 pi RC. But is asking in radians per second. Then omega L, lower cutoff frequency, omega L is equal to 1 by R into C. What is R? 1K. What is C? 1 micro, which is nothing but 1000 radians per second. What is the answer? High pass filter and 1000 radians per second. Whatever may be the cutoff frequency we can find, but remember qualitatively we can solve the problem. Because sometimes, every time, yes, it will take time to write the transfer function. This is theoretical analysis. But for the objective problem, sometimes we need to calculate directly. We should be able to answer directly by seeing the circuit qualitatively. What is that? I am explaining method 2 to solve the problem. What is method 2? Just listen. For low frequency, if you take frequency axis, this is what your frequency axis. Let us say frequency is equal to 0, and then let us say frequency is infinity. That is what is enough. When I say frequency is equal to 0, for DC, capacitor acts as an open circuit. When capacitor is acting as an open circuit, then it is simply what? There is no current. Current entering into op amp is 0. Therefore, this 0 will come here. This is 0. This is 0. Everywhere 0. Then V0 is equal to 0. Therefore, your output is 0. Your output is 0. It is independent of your input. Now, at very high frequency, when input is at very high frequency, means your capacitor is short circuit. Then this VI will come here. When this VI is coming, this VI is coming. Then you will get V0 with respect to VI. That is nothing but 2 into VI you will get. Therefore, you will get here V0 is equal to 2 into VI. Therefore, what does it mean? At low frequencies, it is not passing your input signal. Your output is 0. At very high frequency, your output is function of your input. Means, low frequencies it is not passing. High frequencies it is passing with the gain of 2, let us say. Then, because of op amp, then it is active filter, but it is high pass filter. It is not passing low frequency signals. It is passing high frequency signals. Okay. Qualitatively, I can say that it is high pass filter. But if you ask me what is cutoff frequency, for that I cannot explain qualitatively. For that we should know this is nothing but your passive high pass filter. Whatever signal which you are getting here, that is what is amplified by your op amp, which is nothing but 1 plus R2 by R1. 1 plus R2 by R1 is nothing but 10k by 10k, 1 plus 1 2. Whatever signal you are getting here, that is what is multiplied with the gain of 2, and that is what you are giving it to output voltage V0. This is not only doing amplification, it is also doing buffer action, because whatever load you connect here, that load is not appearing to your 1k. Practically if you directly connect load here for passive network, then this 1k in parallel to the load, it will change the cutoff frequency of your RC circuit. To do not have loading effects for your filter, passive filter, if you use op amp and having some gain, let us say 2, then whatever load you connect, that load is not appearing to 1 kilo ohm, then whatever lower cutoff frequency which is what is defined by your RC circuit, that is what is the lower cutoff frequency which is what is defined by your active filter, active high pass filter defined using op amp. Okay, take it. Qualitatively I can say high pass filter, but this is active high pass filter. This is nothing but your active filter. This is active. Why active? There is a gain of 2. There is a gain of 2. This is nothing but your gain. Therefore, if you calculate, you will get this is what is 2. Okay, active high pass filter. Sometimes there are problems saying the type of filter only. There no need to do all these things, no need to apply nodal analysis. Just directly take frequency scale, low frequency, zero frequency, what is your output? Very high frequency, what is your output? Or sometimes medium frequencies, what is your output? Then we can say the type of filter qualitatively. Okay. Over. If this is over, problem number 13. This is GATE 2007 for 4 marks. This is linked answer problem. Okay. Z is nothing but 0, P is nothing but pole. Okay. Over. Problem number 13. Write down. Consider the op-amp circuit shown in figure. Then problem number 1 from 13 problem. The transfer function V0 of S by VA of S. Asking for transfer function. And if VI is equal to V1 sin omega t and V0 is equal to V2 sin omega t plus phi, then minimum and maximum values of phi in radians are respectively. Okay, take this problem. Problem number 13. This is not writing. Circuit is given. Okay, this is what is given. Then asking for first bit. Transfer function V0 of S divided by VA of S. Option A, 1 minus SRC divided by 1 plus SRC. Option B, 1 plus SRC divided by 1 minus SRC. Option C, 1 by 1 minus SRC. Why I am giving options, I'll tell you. 1 by 1 plus SRC. This is what is problem number 1. Now problem number 2. This is linked answer problem. What do you mean linked answer problem? I'll explain. First of all, if VI is equal to V1 sin omega t, if VI is equal to V1 sin omega t and V0 is equal to V2 sin omega t plus phi, sin omega t plus phi, then minimum and maximum values of phi, minimum and maximum values of phi. You have 4 options. Okay, I am not taking the options. Therefore, now what does it mean? If you observe, the linked answer problem is nothing but the name itself is saying linked answer problem. Means the first bit answer is required to solve the second bit. The first bit answer is required to solve the second bit. That's why linked answer. That is the reason why if first bit is wrong, second bit won't be evaluated. Only if first bit is correct, then only second bit will be evaluated, which I already explained before. Okay, and that is making sense also. If this is wrong, definitely this will be wrong. No need to evaluate. If this is correct, because we are going to use that to solve the second bit, therefore definitely second bit could be correct or wrong. Okay, that's fine. This is for 4 marks. How will you solve? Doesn't matter, op-amp problem. When I say this is op-amp problem, and if you see the options, why I am listing out the options here, if you see the options all are in S domain. Basically, we need to find the transfer function in S domain. That is what is asking. Then later on, we need to get the phase response. That is what is asking. This part I will explain later, but the first one, to solve the first one, to get the transfer function. Then negative feedback and positive feedback, negative feedback, right? Virtual current concept, yes, we don't know this voltage, let me call this as VA. We don't know this, both are same because of virtual current concept. Now apply nodal analysis. If you apply nodal analysis, what do you get? Let us apply here the first equation. VA minus VI divided by R plus, by this time you should draw nodal analysis completely using op-amp problems. VA minus 0 divided by 1 by SC plus current entering into op-amp is equal to 0 is equal to 0. Then what you get? you will get VA minus VI divided by R plus what? SC into VA is equal to 0. If you take VA common, you will get 1 by R plus SC is equal to VI divided by R. If you take R common, R will be cancelled. Then what is VA? If you take VA, you will get 1 by 1 plus SCR is equal to VI. Then VA is equal to VI divided by 1 plus SCR. This you can call it as equation 1 because we got what is VA with respect to VA. Now apply nodal analysis at the other node. When you apply nodal analysis at the other node, let us say then VA minus VI divided by R1, this minus this divided by R1. Now VA minus V0 divided by R1. Therefore now current leaving from this node, VA minus V0 divided by R1 plus current entering into op amp is equal to 0. R1 will be cancelled. Then you will get 2VA minus VI is equal to V0. Therefore, what is V0? V0 is equal to 2 times of what is VA? We got to know already. VA is nothing but VI divided by 1 plus SCR minus VI. If you take VI common, you will get 2 divided by 1 plus SCR minus 1. Then if you take 1 plus SCR as LCM, then you will get 2 minus 1 plus SCR. This VI you can take this side. Therefore V0 by VI. Then what is this value? Therefore V0 by VI in S domain is equal to 2 minus 1. 1 minus SCR divided by 1 plus SCR. This is the answer. Therefore, what is the answer? 1 minus SCR divided by 1 plus SCR. Option A. Listen, what is this? Problem is over, but we should understand the theory behind it, right? Let's see. If you draw Bode plot, what is Bode plot? Basically, this is what your frequency, right? It has 0. 1 minus SCR is equal to 0. Therefore, SCR is equal to 1. S is equal to 1 by RC, right? There is a 0. Now, there is a pole. But 0 and pole are exactly the same frequency. Therefore, there is a pole and 0. Then you know what will happen? Till that point, till you see pole or 0, wherever you see pole, minus 20 dB per decade. Wherever you see 0, plus 20 dB per decade, then both will be cancelled. Then you will get like this only. You will get 0 dB per decade. This is what is 0 dB per decade. Both will be cancelled. Pole is exactly cancelled with 0. Then you are getting frequency response flat. Assuming op amp is ideal. Op amp is ideal means bandwidth is infinity. But practically it is limited by op amp frequency response. But I am not explaining those things. Assuming that op amp is ideal, then this is nothing but what? This is nothing but all pass filter. This is nothing but all pass filter because it is passing all signal frequency components from input to output without any attenuation. Your gain is flat. If gain is flat, what does it mean? Your output is equal to input, right? Your output is equal to input. If output is equal to input, that is what you are calling it as all pass filter. Then simply wire is nothing but all pass filter. What does it mean? If you take a wire, give input, you will get the same output, right? Then why do we need again op amp? Then again calling it as all pass filter, where output is equal to input, it is passing all frequency components. Then how it is different from a wire and then having big complex circuitry like op amp, resistors, capacitors and all. Remember, that is what we will understand. Yes, this is all pass filter, but this is magnitude response. This is magnitude response. What do you mean by magnitude response? This is what is your magnitude response, but this is what is used to give a delay. We want a delay element. This is nothing but a delay element, analog delay element, passing all frequency components with some delay. Therefore, your input is equal to output with some delay, right? That is what is your delay element. Therefore, if you take a wire, there is no delay, input is equal output. But here, input is equal output with some delay. But what is the minimum delay and the maximum delay you can get? That is what is second bit. See, Vi is equal V1 sin omega t and V0 is equal V2 sin omega t plus 5. If you give a sine wave, I am getting sine wave with some delay or with some phase shift. Then asking for what is the minimum and maximum phase shift you can get. Minimum and maximum phase shift what you can get from the all pass filter circuit. Okay. Strictly speaking, the phase response should be linear. Then you'll get fixed time delay, which I already explained. Right? Okay. Take it. Then we need to calculate the phase response from this. Take S is equal to j omega, try to get phase response. Then if you substitute omega is equal to 0 and omega is equal to infinity, you'll get minimum and the maximum phase shift. That is what is asking in the second bit. Therefore, to solve the second bit, we need first bit a transfer function. Then only we can solve the second bit. Okay? Take it. Done? Now let's see the second bit. Therefore, according to second bit, what is your transfer function? H of S. We got it right. 1 minus SCR divided by 1 plus SCR. Right. Then what is H of j omega? H of j omega is equal to 1 minus j omega RC divided by 1 plus j omega RC. Okay. Now what is phase? Therefore, then the phase angle is equal to minus tan inverse omega RC minus tan inverse omega RC, which is nothing but minus 2 tan inverse omega RC. Right? Because tan inverse B by A minus tan inverse B by A. Therefore minus 2. Therefore tell me, when omega is equal to 0, then what is your phi? Phi is equal to 0. When omega is equal to infinity, then tan inverse infinity 90, 2 into 90 minus 180. Therefore this is minus pi. Therefore what is the answer? Minimum and maximum values. Minimum and maximum values, you can say, what is the answer? Minus pi and 0. Minus pi and 0. Option C. Therefore answer is C. Therefore this is what is having linear phase response. If this is over, problem number 14. Try to solve on your own if this is over. Problem number 14. But theoretically, if you ask me what is this? This is all pass filter but providing some delay. Okay. Then time domain delay is represented in frequency domain phase shift. But the phase shift should change linearly with respect to frequency. That implies constant time delay in time domain. Done? What is that? The op-amp circuit shown in figure represents dash. Option A high pass filter, option B low pass filter, option C band pass filter, option D band reject filter. I told you, right? There are problems saying that asking for type of filter, then qualitatively we can solve. No need to write transfer function. Yes, if you write transfer function also you'll get it, but no need to write. Problem number 14. This is R1, L. This is C, R2. Right? Option A high pass filter, option B low pass filter, option C band pass filter, option D band reject filter. You can have all pass filter also, which we had seen before, and we had seen high pass filter also. Let's see what is this. We can solve this problem qualitatively. Qualitatively in the sense, no need to write transfer function. Actually, if you want, you can write transfer function. Nodal analysis, 0 minus Vi divided by Z1, 0 minus V0 divided by Z2 is equal to 0. Z1 is nothing but R1 plus SL, Z2 is nothing but both are in parallel. If you solve, you'll get it. You'll get zeros, poles, based on that we can get it. That is fine. But qualitatively you can solve, because not asking for cutoff frequencies. If they are asking for cutoff frequencies, then we have to write transfer function using nodal analysis, you will get it. But qualitatively you can solve the problem. I told you, right? How will you solve? This is your frequency part. Let us say f is equal to 0 and f is equal to infinity. Right? Now, when I say f is equal to 0, DC. For DC, inductor acts as a short circuit. For DC, capacitor acts as a open circuit. Then tell me. Then resistor is there, resistor. Then R1, R2. Then what is V0 by Vi? Minus R2 by R1. If you take only magnitude, then your V0 is something into Vi. Therefore, it is passing your input signal. That is fine. Now, let's see very high frequency. For very high frequency, it is open circuit. For very high frequency, this is short circuit. Therefore, this is open, this is short. Therefore, this is short. Then negative feedback is there. Virtual current concept is valid. Then you'll get 0 here. Then 0 is coming at the output. Because this is open, this is short. Therefore, this is short circuit. Then the 0 will come here. Then V0 is equal to 0. Your V0 is equal to 0. What does it mean? It is passing low frequency signals, not passing high frequency signals. Your output is equal to 0. This is nothing but what? Low pass filter. Answer is B. Okay, done. Write down problem number 15. Over, right? Or maybe before going to problem number 15, because yes, you are able to solve the problem, but if you want to solve the problem theoretically, maybe we can write the transfer function, because it's not only to solve the problem, we need to understand the theory also. Okay, now let's see. As I told you, yes, negative feedback, then this is what is 0, then apply. Let me take this as Z1 and let me take this as Z2. Now no need to apply nodal analysis, basically you'll get it, right? This is nothing but what? This is equivalently represented as minus plus, this is Z1 and this is Z2, this is V0 and this is Vi. Then what is V0 by Vi? It is nothing but inverting amplifier, right? Minus Z2 by Z1. That's it. Therefore, what is V0 by Vi? V0 by Vi is equal to minus Z2 divided by Z1. What is Z2? That's what we need to get. Therefore, Z2 is nothing but, both are in parallel, right? R2 into 1 by SC divided by R2 plus 1 by SC. R1 R2 divided by R1 plus R2, like that. Therefore, SC will be cancelled. It will be R2 plus 1 by SC into R2. This is what is Z2. Similarly, Z1 is nothing but R plus S into L. Then you put it minus Z2 minus R2 divided by 1 plus SC into R2 divided by R plus S into L. Right? Then what is this? If you take this, you will get minus R2 divided by this is R1, okay? This is R1. Then what you will get? R1 plus S into L, 1 plus S into C into R2. Okay? Then if I take R1 common, what I'll get? From there, V0 by Vi is equal to, if I take R1 common, you'll get minus R2 divided by, if you take R1 common, what I'll get? I'll get 1 plus S into, excuse me, L by R1, right? Into, if I take R1 common from the circuit, R1 into 1 plus SL by R, that's it, then 1 plus SC R2. Then what is this? This is nothing but minus R2 by R1 divided by 1 plus S into L by R1, 1 plus S into C into R2. Therefore, what is this? This is what is our DC gain, but if you ask me the plot, we have two poles, right? One pole is at L by R1, one pole is at R by L, R1 by L, and another pole is at R to C, right? Therefore, let us say this is what your pole P1. P1 is nothing but 1 by R1 by L, R by L. Then what is P2? Let us say pole P2 somewhere. Let us say this is what is P2. We don't know the values, but let us say P2. P2 is equal to 1 by R2 into C. 1 by RC. This is what people call it as 1 by L by R. L by R is nothing but L by R1. Right? Then up to the pole, Bode plot. There is nothing. Pole 20 dB per decade minus 40 dB per decade. Right? Therefore, let us say this is what is slope minus 20. I just took P1 is less than P2. Then what is this? This is what is 0 dB per decade, and now this is minus 20 dB per decade, and now this is what is having a slope minus 40 dB per decade. What out maybe? This is nothing but what? It is low pass filter. It is passing low frequency components and not passing high frequency components. But this is second order low pass filter. This is second order because it is having two poles. Second order low pass filter. Okay, take it. I think time is over for this session. We will continue in the next session. Meantime, you can continue or you can take transfer function. This is basically second order low pass filter. Having two poles, and this is what is called DC gain. Maybe if you speak with respect to control systems, G of S is equal to K divided by 1 plus S into S by P1 and 1 plus S divided by P2. We have two poles and having a gain K. This is what people call it as K or DC gain or low frequency gain. That is what is your DC gain, low frequency gain. If you speak about only magnitude, mod V0 by Vi, right? This is nothing but R2 divided by R1. This is what people call it as K. Then when you do this is what is open loop system, right? If that is not stable, what does it mean? If K is varying, why K will vary? Let us say R2 by R1 is varying. If R2 by R1 is varying, then to stabilize the gain, we will apply negative feedback. Therefore, when K is varying from 0 to infinity, then what is the closed loop system stability? That is what we are doing. Therefore, when I say K is nothing but DC gain or low frequency gain. That is what people say. But practically it will not change from 0 to infinity, but even if it changes from 0 to infinity, your closed loop system should be stable. That is what is called always stable. Okay. For few values of K, that's what we have seen, right? 3-pole system. For few values of K, some poles are entering into right half of the S plane. You understand? I explained, right? That is what. Few values of K means for few values of K, R2 by R1. Let us say you are choosing different R2 by R1, then the system may be stable, may not be stable. But whatever may be, this is what your total system. Assuming that your op amp is ideal. But if you take practical op amp, it has a pole inside because op amp is dominant pole system, and then it is having 2 poles. So overall, it is having 3 pole system. 3 pole system may be stable, may not be stable. That's why we need to see. Then normally people say P2, if you put it to higher side, you will get it. Whatever may be, assuming that op amp is ideal. But if you consider practical op amp, then overall it is 3 pole system, because in feedback we have 2 poles and op amp is 1 pole, overall 3 poles. The system may be stable, may not be stable. That depends on the value of K. But normally if you choose the value of K such that it is always in the left half of the S-plane, system will be stable. Because K is in your hand, and that too even the temperature changes and all, R2 by R1, the ratio is constant. If ratio is constant, then due to temperature, the variation of K is not like 0 to infinity. Until unless you explicitly choose values of R2 and R1. Okay, that depends on the gain requirement. If you want more gain, you will lose the stability. If you want to choose lesser gain, you will get more stability. That is always true. But when I speak about gain, that is nothing but low frequency gain. Okay, time is over. Then we will continue in the next session. Thank you.